Hey guys, Jack Plone back with another video upload for Hopkins, and we're just going to dive on right in with the instructions and what we have to find. So first of all, we have to show how to do a Lewis structure, just like get a deep explanation just so I can fly through it the next times. Then we have to find the partial charges on all the molecules we've been given and the bond dipoles, and lastly just find the net molecular dipole. Okay, so we move on to this first one. First step to creating a Lewis structure is finding all the valence electrons in those atoms. You add beryllium has 2, and then you have 2 chlorine atoms, which both have 7 valence. So you have 16 valence total. That's 14 plus 2, 16. So 16, you can basically assume right off the bat that it's going to be 8 and 8 because you need to give the outside atoms the 8 first. It's the octet rule. And the BE is actually a violator of the octet rule. So you just give these 8 and 8, and then you're left with that. You give the beryllium 2 bonds, and it's fine with that. You go ahead and you actually do the formal charges for these, and you get 0 all around. So it ends up being a perfect. That's the best form it possibly could be in. So that's why it's allowed to violate that rule. It's one of the few atoms that actually violates it. So then we go ahead and we go into the bonds, and we know that chlorine is actually more electronegative than beryllium, and we can do this by consulting with the periodic table, which chlorine is more to the right on the same row as beryllium, chlorine is. So for that reason, it has a higher electronegativity. So the dipole, the electrons are going to move closer to these chlorine atoms, and so there we go for that, and that's why it has a partial negative charge, and that's because the electrons tend to move in that direction. So there we go, and these bonds actually cancel out because they're going in opposite directions and they're the same atom, so equal force, same amount of electrons and everything, so they're non-polar because they have no net dipole movement, so they cancel out. And just the structure you actually need to calculate in order to get the dipole movement, like the molecular geometry is linear, and that's just because it's just 2 bonds, that's it, simple as that. And so just 2 simple bonds, nothing unbonded. It's linear, straight across. So then we go into this molecule, which is oxygen and 2 fluorine atoms. So we get a similar structure to that, except the oxygen, which is not an octet violator, so it has to have the amount, which you have. You fill out the fluorine, and then you have 2 unbonded pairs left to put on the oxygen and give it 8, so it applies to the octet rule. And the next thing you have to go ahead and find is just which one are partial, which one's negative partial charge, positive partial charge, so you know in the direction they'll be heading. But don't forget to find the molecular geometry, which is bent because it has 2 unbonded pairs and 2 bonds, which is 4 total domains and just 2 unbonded, 2 bonds. So these actually head in opposite directions, but because they're y-axis in which they move down, they have a polar charge because they move down. And it's bent, as you can see here, because the 2 unbonded, which repel these in the opposite direction. And just something also that you should understand by now is that the fluorine atoms obviously have the electronegative charge, which is why they are partially negative, because the electrons tend to head in that direction. Okay, so moving on to the next 2. Okay, so here we are with SO3, and so that's 1 sulfur atom and 3 oxygen atoms. So we get this basic Lewis structure. I always just start off with the basic Lewis structure before going on to the molecular geometry. So we have to give 8 to the outside pair, which you do so. You get 2, you would normally have 2 here, 2 here, 2 here, and just 3 bonds between the oxygen and sulfur. Just 1, 1, 1. But you go ahead and you notice that you can actually put double, and you actually give the S the amount of, you give more than 8 electrons actually in its shell, but S is actually an octet violator, so you're allowed to do this. You're allowed to give it more. If you notice, if you do the formal charges for this, these already had 0. Actually not, they didn't in fact have 0, but this one will now have 0 because it has 6 valence electrons. Here, I'll go ahead and write it out. S normally has 6, and we subtract it from the unbonded pairs, which is 0, has no unbonded ones, but it also has the number of bonds, has 6 bonds, so it gives it a 0 formal charge. So you know this is the best possible configuration you can have. So then we go to find the molecular geometry, which happens to be trigonoplanar. So there you see there, it's a little difficult to see the formal charges in terms of that. You should know that though S is directly below it in the column for oxygen, S actually has a less electronegative charge because it's on the lower row. And so there we have the oxygen being more electronegative. And these go in all separate directions, and though it's difficult to see, they actually all cancel out because these have somewhat of an upward force, which is, configured in between here. These opposite directions actually cancel out. These cancel out, and then this upward force between these two is canceled out by that downward force, which is in this oxygen atom. So then, as I said, trigonoplanar, everything, because 120 degrees between them, and you just know that because it's just 3 domains, no unbonded pairs. So then we go into the last atom, which is actually trioxide, and so it actually ends up being a resonance structure. We have the oxygen here, single bond, double bond, and then also you can just switch the double bond to this side for it. So you get partial negative, partial negative, partial negative, partial negative, and positive. Just the way it goes, because it ends up moving away from it. So that's how you know that. Also, these have more unbonded electrons on them. So that's just something you can kind of point out, just give a reasoning for why these ends up being more electronegative for that. So just off on a side note, this is actually what it looks like if you were to represent it. It's actually a dotted line because realistically this double bond is shared among these two, so these actually each have 1.5 bonds, so you can see here. But just going into what we were supposed to find, we have these two in this direction, and as we've seen before, when they go in that direction, there's a general downward force. The opposite, the x directions cancel out, these cancel out, and we're just left with the downward force that these have displayed upon the molecule. So there we go, we have a bent, and it is polar because it does have a net dipole, which is going downwards. And so we go into the common mistakes now. And so common mistakes are neglecting octet violators, such as we've seen here. This is an octet violator, it can have more than 8, and as we saw earlier, this beryllium actually is given less than 8 in order to get the perfect molecule, which has a formal charge of 0 on all atoms. Then incorrectly counting the valence electrons. If you were to incorrectly count something, like as shown here, if I were not to get this number correctly, I would completely create a false Lewis structure and completely throw the entire thing off. I would mess everything up. So that's the most important thing, is knowing your valence electrons, how to count them on the periodic table. Also, a side note, same thing for electronegativity. You need to know which one goes for that. So that electronegativity included with that. And then finding the dipole movement without knowing the molecular geometry. For instance, if we look at this one, this is a perfect example. If we just drew the Lewis structure, we would just do linear, which would be completely incorrect because these two unbonded on the oxygen, it forces the fluorine down, creating a bent structure. So in normal, if we just did this one, we would get this kind of dipole movement, and you would just assume these would cancel out, and you'd assume the molecule is dipolar, non-polar. But it's not. It's actually polar because of the downward force among these two. And that covers it for the common mistakes. That's everything. Thank you.